Shut up and sit down.
Well, hey everybody, welcome to another episode of Master the NEC, where we talk about the National Electrical Code, of course, all things electrically related. My name's Paul Abernathy, your host as always, and welcome to the podcast. Now, in today's episode, we're going to talk a little bit about a definition, but we're also going to get into the concepts of this definition and the reality of how you would use it and explain it in the real world, because there's a lot of people that still have questions about what is ampacity. So today's topic, we're obviously going to talk about ampacity. We're going to kind of define it. We're going to look and see how it takes a role in what we do, whether it's residential, commercial. So it's across the board. Ampacity is what it is. And we'll talk a little bit about how it used to be the allowable ampacity. And of course, we removed that from the National Electrical Code because allowable was kind of a notion that even though it was adjusted or corrected, there was this allowable, and it's really ampacity is ampacity, okay? And so we'll get into that in details, but before we do that, we want to listen to a word from our sponsor. Again, hopefully you visited electricianpride.com, and we've got some really, really great new logos, Code Strong, we had the Code Mafia, we have Code Warrior, and we just have some great stuff over there, so I want you to check it out. But again, I'll run the commercial, and we'll get started on the episode right after this. Today's show is sponsored by electricianpride.com, your one-stop shop for electrician-specific t-shirts, hoodies, phone cases, mugs, die-cut stickers, leggings, and so much more. Featuring unique designs for electricians, journeymen, and master electricians, as well as electrical engineers and electrical inspectors. For more information on all the products that are available, visit us at www.electricianpride.com today. All right, so let's go on and jump into our discussion for this episode of the podcast. So we're going to be talking about ampacity, and we're going to try to explain ampacity to get a better understanding of what ampacity is and how you might need to understand it as you start to work throughout the NEC, because the term ampacity, now obviously it's in Article 100 definitions, so it's used in more than one article. Okay, so that's a given. And once you understand definitions, in this case ampacity, then it's so much easier to be able to apply it to different areas of the code where this term will pop up, and you have an understanding. You're like, okay, I understand what ampacity is. Then, of course, we have to understand adjustment and corrections and everything, ambience and all these type of things. But you really need to understand the basic core fundamental understanding of ampacity. And I routinely see this discussed improperly, and I figured it would be a good, quick podcast to be able to try to explain it without getting too deep into the weeds, because we have a whole series that's coming up in 2021 on these type of things. So let me kind of get into it. Now, before I even start, I want to say we're in the 2020 National Electrical Code on this episode. We're in Article 100 for definitions right now, and we're in Part 1. Now, definitions, Article 100 is 3 parts. And for the 2020 code, Part 3 was new, which is basically taking all the hazardous classified location definitions and moving them over to a Part 3, which makes them nice and logical in where you go to find all of the things that you need to know about hazardous classified locations, for Article 500, 501, 502, 503, blah, 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 blah. All right, so those definitions are going to be very concisely situated in Part 3. Now, of course, Part 2 is for all those over 1,000-volt applications, and of course, Part 1 is a general, and we're going to be working out of the general to start with. Okay. All right. So let's look at Part 1, general, and we're going to go down to ampacity. Now, it's very important that we understand what ampacity is at its root core. That way, when we encounter it, we understand what it means. Now, it used to say in the code, and most notably over on 310.16, which used to be 310.15b16, it would tell us that allowable ampacity. And again, that was kind of a misnomer, if you will. Allowable is very, how should it say? It's subjective. Truth of the matter is allowable just didn't work. And so an ampacity is what it is based on the conditions of use. So if you follow all the conditions of use, and we'll get into that under 31016, the ampacity table, then under that conditions of use, those values there, depending on the terminal ratings or the temperature ratings, 60, 75, or 90, that is the ampacity. Okay? That is it. Now, when you apply some type of adjustment or corrections, maybe in 31015B1 and in C1 of the NEC, whether it's ambient temperature corrections or number of conductors adjustments, that's going to change the ampacity of that conductor because those are considered conditions of use. Now, there are other conditions of use, like continuous loads and things like that we have to take into account. All these things are conditions of use, okay? So we'll kind of touch that when we get a little further into that, but let's kind of draw ourselves back and stay in the definitions, and let's truly understand what ampacity means. So the definition reads as this. It says the maximum current, okay? The maximum current in amperes that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. So, if you were to look at table 31016, okay, and of course, you also have section 31016, which corresponds to the table, it will give you the conditions of use to be able to use that ampacity, which is the maximum current in that table. So under those conditions of use, as specified by the table, not more than 3 current carrying conductors, 86 degrees Fahrenheit, 30 degrees Celsius, if that is your temperatures and that is the situation with the number of conductors, then that ampacity given based on the temperature limitations, that is the ampacity. That is the maximum current that conductor can carry under those conditions of use. Of course, you and me both know that terminal limitations in 110.14c are going to come into play. We also know, again, you have the ambience corrections. You have the number of conductors adjustments that might have to take place. But it's just important to understand when we're talking about ampacity, it's the maximum current in amperes that a conductor can carry. Okay? The maximum current. So when you try to put those two things together, it really starts to help you understand that anything else that we do, we calculate loads, we have connected loads that ultimately apply some type of demand factor and becomes a calculated load, or we do something to come up with an end value, and now we take that calculated load, which is different than a connected load, and then we have to go searching for conductors. And then, of course, we have to also search for overcurrent devices to protect those conductors, right? And the whole concept is to protect those conductors during its condition of use so that it basically doesn't exceed the temperature rating that is on that conductor. Simple, right? So if I have a conductor that's got a 75 degree rated insulation and I have to apply an adjustment or correction to it, the reality is those things can create heat, and the heat could get us to this point where we violate the rating of the insulation. And of course, then you have a condition where it starts to break down. So in order to adjust for that, we have adjustment and corrections to be able to say, basically, we're going to lower the amount of current that conductor can carry. In other words, we're going to lower the ampacity that conductor can carry based on conditions of use. And so it will have a new maximum current in amperes that conductor can carry under those specific conditions of use. If you think about it, it's a beautiful thing because you have a conductor that has an ampacity. It's in 31016. Of course, there's other tables as well for other different types of applications, 310.17, 310.18, blah, blah, blah. But our most used table is 310.16. And so if you think about it, that is your ampacity. But any time that you have to apply some type of condition of use, and again, we discussed what those are, at that point, you will get a new ampacity for that conductor. And that will now be the maximum current in amperes that that conductor can carry continuously under that condition of use. Now, again, we also have to remember that things like continuous loads are going to change that. That is a condition of use. Again, ambient temperatures above the normal, 86 degrees Fahrenheit and 30 degrees Celsius, that affects it. Of course, above it and below it can affect it. Going below that, cooler is a benefit to you, believe it or not. You will actually gain some benefit. But when it gets hotter, it's never going to be a benefit. Okay, heat is never a good thing when it comes to current flow. Okay, because the current flow is going to create heat on itself. So you have other conductors or other cables, and that's where bundling comes in. You end up getting what's called mutual heating, and that is never good for ampacity. It's always going to result in a lower ampacity. So you end up with a conductor that's not going to have the same current carrying ability as it might have had before you applied those conditions of use. You with me? So that's why it's so important. So knowing that it's the maximum. Now, what does the maximum current, okay? That is one of the things, the maximum current in amperes that a conductor can carry continuously. 310.16, and we're going to go to that because we're really off of the definition right now. Let's go to 310.16 because I want to explain something to you. Now, if you're on 310.16, you'll all notice that for the 2020 edition of the NEC, if you're on that table and you're in the 2020, look on the left page. You'll see that there is a 310.16, 310.17, 310.18, 310.9. You'll see that it's there. The conditions of use are over here in 310.16. Okay? So, yes, at the top of the table of 310.16, we have, again, one of the conditions of use still stated in the actual header of the table, which is with not more than 3 current carrying conductors in a raceway, cable, or earth. Yeah, but the real conditions, and it's also stated again over in 310.16, the real conditions are broken down into 4 items, okay? And so if you're looking at 310.16, it says conductors are rated 0 volts through 2,000 volts, okay? So that's what we're dealing with in 310 is 2,000 volts or less, okay? So we're setting that tone. The next one is conductors are rated 60, 75, or 90. Again, all based on the insulation, all based on what you get. Again, not forgetting the requirements in 110.14c for terminal limitations, because again, the weakest link thing is going to approach. If I use a conductor with an insulation that is 90 degrees, but my terminals are rated 75, then I've got to base everything on the 75. Even though I can use the ampacity value of the 90, but I have to apply those what? Conditions of use. And if I apply those conditions of use, all we're trying to do is make sure that we still have a conductor, 1, that can handle the load, and 2, that is protected in accordance with 240, which is the overcurrent protection rules. Okay? So you have to understand that this table, these ampacities that you see right here on the table, this is the ampacity. We don't have to say allowable. This is the ampacity under these conditions of use. Now, also should remind you that it can pull these ampacities continuously, indefinitely, and not violate the rating of the insulation, not cause a breakdown. If you follow these rules, okay, in a perfect world, again, you're not more than 3 current carrying conductors in a raceway or cable or in the earth together. If your temperature is not, if its installation is 30 degrees C, or 86 degrees Fahrenheit, and again, not more than 3 current carrying conductors, the ampacity that you see in this table, you could pull indefinitely, and it would never violate the insulation rating. Okay? It's already been figured out for you based on this condition. There's enough allowance of dissipation. You don't have to do anything. Now, we live in the real world, and we understand that conditions of use are everywhere. So you might run those conductors inside of a raceway that goes through an area, or in a cable that goes through an area with an elevated ambient temperature. So you're going to have to make a correction for that. If I run them bundling, there's rules in 310.15b that say, well, you know what? If you're going to run those conductors and you're going to be bundling them, you got to take into that account. If you're, C 310.15c is the one for adjustments. B is the one for ambient. So if you're running a bunch of them bundled and you're more than 3 current conductors, then you're going to have to do something, right? That's what 310.15c1 is telling you. If I'm running those conductors or those cables in an area that has an elevated ambient temperature that is not 30 degrees C or 86 degrees Fahrenheit, then I'm going to have to do something to that ampacity. I'm going to have to think about, okay, well, the temperature is too high. I'm going to have to make a correction. And why are we making a correction? Because we're going to end up ultimately lowering the ampacity in most cases. We're going to lower the ampacity of that conductor so that as that conductor is pulling current, it's not going to heat up and it's going to actually cause problem and violate the insulation's rating. Okay? So as you can see, when we do all this, it's a magical dance that you have to do. And, that I like to tell people, that's why electricians get the big bucks, right? We have to think about those things. And so you always have to be it. Now, the beautiful thing about it is that, for example, if you're going to do temperature corrections, then it's pretty simple because in 310.15b1, we have a table. And this table is a 30 degree C, 86 degree Fahrenheit. So this is what corresponds with 310.16, okay? Because we're basing it on 30 degrees C and 86 degree Fahrenheit. Now, a lot of people ask, there's a 310.15b2, and they say, what is that all about? Well, that one you're going to pretty much use with different tables. For example, if you were to go back and look at the 310.16.17.18.19, you're going to see that 310.16.17 deal with the 30 degrees C, 86 degree Fahrenheit. But when you get to 310.18.19.20, you're going to see that they talk about 40 degrees Celsius. So typically, those tables are going to work with table 310.15b2. But the one that the majority, if not 99% of the electricians out there are going to deal with, that's going to be 310.15b1 ambient temperature correction table. That's going to be your predominant workhorse. In fact, I do know people that teach people on exams to mark out 310.15b2, and I tell them don't do that because it would be just your luck you get on an exam and they ask you something based on that table, based on one of the other tables, like 310.19 or something like that, and then you're sitting there with a marked out table in your code book. I don't recommend you do any of that kind of stuff. So anyway, that is pretty simple. Now, the interesting thing about that table now is that you use, this one here is based, when you look at it, it is giving you values that you multiply by, okay? So this is a correction value. And for example, if I was doing THHN in a raceway and I had an ambient temperature that was higher, let's say 114 degrees. So that's higher than 86. So it's 114 degrees. Because that insulation is rated for 90, THHN, when I come over here to apply my adjustment and corrections, I apply it to the 90 degree column. So this is where I get my values. So you take whatever the ampacity is from 316, you multiply it by your actual correction factor. In this case, since the insulation is rated for 90, I use the 90 degree column. Keeping in mind that if your insulation is 75 or 60, you would use those columns, okay? You can only use the column that's equal to the rating of your insulation when you're doing this adjustment and correction. Now, the code allows me, okay? The code allows me to use the 90 degree for adjustment and correction purposes. It says that right after 310.15a, okay? So that shouldn't be new to anybody. But always remember that you can't exceed the ratings of the terminal limitations, and they're going to correspond typically with 60 or 75 degree, depending on the ampacities, under 100, over 100, okay? So, again, we have a video on that called Derating Demystified. I am updating that for the 2021 year, but it is available right now over on our YouTube channel. Go over and look for it. Just write Derating Demystified in the search bar on our channel, and it'll come up, and you'll be able to find it. But it's also underneath the playlist for electrical calculations. Okay, so if you want to jump on over there, feel free to do that. Now, when it comes to the number of current carrying conductors, assuming that we exceed 3, then we have to do what is called an adjustment factor, because each one of those conductors put out heat, and it's called mutual contribution. And so you have to make an adjustment accordingly. Now, over here, you'll notice that it's in percentages. It's not broken down like it is in 310.15b1, where it's already in the decimal format. But over on 310.15c1, and I probably should have put a public input into that. Why not just put it in the decimal format? But, for example, if it's 4 to 6 conductors, again, we're exceeding 3 in a raceway. If it's 4 to 6 current carrying conductors, then it would be 0.80 or 80%. Of course, we know how to convert that to a decimal. Go from the right, move 2 spaces to the left, 0.80. And that's what we're going to multiply by our ampacity out of the 90-degree column in 310.16 if my insulation is rated 90 degrees. Okay. Now, remember, you typically cannot use the 90-degree rating ampacities for anything but adjustment and corrections, with the exception. Now, what is the exceptions? I shouldn't say exceptions in the code, but exceptions to that rule is that if my terminals are all rated for 90, my wire's rated for 90, then I can use the 90. But usually that's not going to be the case. Usually breakers, the terminals on those, typical terminals and panels and switches and all that kind of stuff, they're going to be either 60 or 75. Okay, so that's going to be your limitation. But there are tap blocks, for example, that might be rated 90. And so I'm able to use that at its 90 for maybe the portion between tap blocks, because those blocks are rated 90. But the portion that goes from the block down to the panel, your limitation is going to be on the terminal in the panel. And that's probably only going to be 60 or 75. So you're going to be limited to that. Okay. Again, go watch Derating Demystified if any of that confuses you. But I'm just kind of giving you a summary of all those things. And again, sometimes I'm known to go too fast for people, and sometimes people say, Paul, you're redundant. I can't please everybody. I've learned the hard way that it's just impossible to do. All right. So in a summary of today, ampacity. It's the maximum current. Okay. So it's the maximum current. Now, with that said, I decided just right now, while we're doing this episode, again, that I'm going to explain continuous load. Because again, I almost feel like I have to put the two together so that you can understand the difference in the two. Because ampacity is what it is. We're trying to find out what is the amp that conductor can pull or handle under that condition of use. Okay. And whatever that value is, that is the maximum current that it can handle. But then you have to remember that's under the conditions of use. So the reason that we got rid of allowable is because it's ampacity regardless. It starts out as ampacity. When you do an adjustment or correction or whatnot, whatever the ampacity of that conductor is at that time, after that, under the conditions of use, that is still just the ampacity. It's what it is. Now, when you think about continuous loads, let's talk about that for a second. Continuous loads is in your code book, obviously in Chapter 1 still, under Part 1. It's on page 34 if you're in the softbound edition. It's near the bottom. Actually, it's at the very bottom of the page. Continuous load. Let's kind of define continuous load because that gives us a good place to end this podcast on. It says, a load where the maximum current, doesn't that sound familiar? That's right. This one's based on the load, however. It says the load where the maximum current is expected to continue for 3 hours or more. Now, this is under the code CMP2. It's under their purview. They're the one that writes those rules, and Code Panel 2 will be the one that creates this definition, and they're the keepers of this definition. So, let's talk a little bit about continuous loads. When I'm in a dwelling unit, and a lot of people think about ranges, and I'm cooking in my oven, and I'm cooking a roast or a turkey during the holidays, and it's going to be on for 4 hours or 5 hours in the oven. And they're thinking, gee, that's pulling current for 5 hours. That's got to be a continuous load. The reality is it's not a continuous load. And we don't treat it as a continuous load because it says a load where the maximum current is expected to continue for 3 hours or more. The maximum current. So if it pulled 50 amps, I'm just throwing numbers now, it would have to pull 50 amps continuously for 3 hours or more to be considered a continuous load, because that's what the load is. No luminaires inside of a dwelling would ever be considered continuous load, even if you leave them on all day. Okay, it's diversity involved. Okay, so there's a big difference. Now, let's kind of remember also that the National Electrical Code will tell you specifically when certain equipment is considered a continuous load. Great example is water heater. A water heater, when it comes to branch circuit applications and sizing and all that for conductors, is considered a continuous load. Now, we would not consider it at 125% when we're doing the service or feeder calculation, but when we're doing branch circuit calculations, we most certainly will take and treat the water heater as what? A continuous load. Now, why do we do that? Is it because that water heater is going to be on for 3 hours or more? Probably when somebody in my house is taking a shower, it probably will be. But at the end of the day, is it a continuous load? And what makes it a continuous load? Okay, well, you only have to do something very simple. And that is go to 422. That's the article for appliances. Obviously, also under code panel 17. I'm on that code panel as well. And if you look at 422.13, it says, point blank, the branch circuit overcurrent device and conductors for fixed storage type water heaters that have a capacity of 120 gallons or less shall be sized not smaller. Okay, so this is the overcurrent and the conductors, not smaller than 125% of the rating of the water heater. Okay, now what's interesting about this statement? It's not saying that it's a continuous load. Okay, it's not saying that it's a continuous load. So why do we treat it at 125%? Because it basically mirrors the requirements for a continuous load, but it tells you to do it at 125%. Don't worry, I'm going to tie it all together. I know you're saying, wait a minute, I'm confused. Just bear with me for a second. So that is kind of the same concept we do for continuous load. Now, there's other areas in the NEC where they point blank will tell you to treat something as a continuous load. And it'll say it in such. And a lot of times we'll run into those things in 424, for example, where it might tell you for certain types of heating and all that you take it for not less than 125%. And again, it's kind of works the same way. So some places in the code, it will tell you to treat something as a continuous load. Some will physically say it's considered a continuous load, and you have to understand what a continuous load is and then how you'd apply it. And I'm going to tie it all together in a second. And then other areas of the code, you will know that you just have to treat something as a continuous load. For example, if I have lighting, a sign lighting for parking lot lights, they're going to be running at their full rating continuously for 3 hours or more, probably 8 hours, probably whatever, all night, if you will, right? Those have to be treated as continuous loads. Now, the beautiful thing about calculations, and I won't get too deep in 220, but 220.12 is kind of incorporated now with its new VA per square foot based on the different types of occupancies and what you're dealing with. It's already going to incorporate the 125%, so it makes your job as a designer a little easier in the 2020. But we always understood that any lighting loads in a commercial building that is on for 3 hours or more is to be treated as a continuous load, right? Kind of. Now, we've made a lot of talk about continuous load. We said a whole lot about it. So I'm going to, since we're talking branch circuits, really, we haven't really gotten into it. We're going to tie this up to where are we getting this information about continuous load? Where is Paul getting all this at? Okay, so if you're in your code books, what we're going to do is I'm going to actually address you to go to 210.19. Now, 210.19, and remember, we understood what a continuous load was, okay? 3 hours or more. 210.19, we have an A, And that says branch circuits, not more than 600 volts. Okay, typical branch circuit. It says general. It says branch circuit conductors shall have an ampacity. We already know what that is, ampacity. Okay, we know the definition. Not less than the larger of 210.19A1A or A1B, and comply with 110.14C for equipment termination. So that's just a reminder that, you know what, you're going to do these, you're going to follow these rules, but you're not going to forget that the terminals are the weakest link in sizing. Okay? Now, there's an A and a B. What does A say? A says is where the branch circuit supplies continuous loads, that is loads that are on for 3 hours or more at its maximum current, or any combination of continuous and non-continuous loads. So I could have a branch circuit that's supplying a continuous load, but some other non-continuous load. So under A, I have to take the continuous loads and I have to take the non-continuous loads. But what do I do with these loads? Let's look at it. It says, the maximum branch circuit current shall have an ampacity of not less than the non-continuous load, that would be at 100%, whatever that load is, and where it says plus 125% of the continuous load in accordance with 310.14. So we take the non-continuous loads that are not going to be at maximum current for 3 hours or more, and we take those at 100%. Whatever the load is, it is what it is. Okay? Whatever the amps are, it is what it is. But the continuous loads are all those loads that will be on for 3 hours or more at its maximum current, or any loads that are demanded to be considered continuous loads. Those are the things that we're going to take at 125%, and you add them together. Okay? So that's A. And whatever conductor that results in, okay, that's whatever conductor. So if A is a certain size conductor, we write that down, whatever that may be. We could say that was an 8 gauge. I don't know. Well, let's just say it's an 8 gauge. Now, you have to look at it and say, does 210.19A1B apply? And what does that mean? It says, well, B says the minimum branch circuit conductor's size shall have an ampacity not less than the maximum load to be served. Okay, so we got to know what the load is after the application of any adjustment or correction factors in accordance with 310.15. So what this is saying is I'm using the ability to apply adjustment and corrections here to where the code lets me use the 90 degree, for example, if the installation is rated for 90. But after I do those adjustments and corrections, after I'm all done, whatever the ampacity is at that point, I size to. And whatever conductor that results in, I compare it to the size that I came up with in 210.19A1A. And as it says, it has to be the larger conductor. It has to be the resulting conductor that's larger when you compare 210.19A1A to 210.19A1B. And whichever results in the largest conductor, that's the one you go with. Okay? Now, what's interesting about this is, what if I don't have any continuous loads? What if they're all non-continuous loads? Okay. Well, if they're all non-continuous loads, then it's just normal ampacity. Okay? I don't have to worry about 125%. It's just basically 100%. That's a non-continuous load. But I would tend to use B because I don't have any continuous loads to utilize A. So I would utilize B. Okay? Because it says any combination, it says supplies continuous loads or any combination of continuous and non-continuous loads. Well, if I have no continuous loads, then I'm going to go right to B. And that's when I would apply my normal adjustment of corrections. And after that, I have to have a conductor that, one, can actually handle the load, and two, not violate the terminal limitations that are in 110.14c. And that's what we do today. Okay? When we don't have continuous loads, we usually end up defaulting when branch circuits to 210.19A1B without you even knowing that's what you do. Okay? But when you do have continuous loads and you have non-continuous loads, or you have continuous loads and you have adjustment and corrections based on maybe the ambient temperature or the number of current carrying conductors, then you have to compare A to B. And whichever results in the largest conductor, that's the one you go with. Pretty simple stuff, right? But that's how you apply it. And so when you wanted to know where we tied this continuous load back, we are tying it to 210.19a. And for feeders, for example, because, I get that question quite often. People say, how do I tie that to feeders? That's in 215.2a1 as well. So again, synonymous with that. And people say, well, I understand that. I get it. It is confusing for some people. That's why I encourage you to go watch our D-Rating Demystified, because it really attempts to try to break all that out. Okay. Now, other people say, okay, I get it, Paul. That's where you do it for branches. That's where you get your explanation for feeders. Where do you get it for services? Well, for services, it's 230.42a1. Same concept. Okay. Just put it different places, whether you're dealing with branch circuits, feeders, or service conductors. Okay. We don't want to overcomplicate it, but that's why it's so important to understand what ampacity is, and then to understand what a continuous load is. Okay. In a dwelling, again, I don't know any continuous loads in a dwelling, to be honest with you. Now you could have some motors that are in the dwelling for branch circuit sizing. Obviously, you're going to follow 430, and if it's a single branch circuit to a motor, you're going to follow 430.22. So that says to take it as 125% of the FLC. You'll have water heaters that'll say to treat it at 125%, which is pretty much synonymous with treating it like a continuous load, because both of them use the 125%. Not to get confused, we're not saying that the code says a water heater is a continuous load. It's just saying treat it like it is by adding that 125%. And to be honest with you, that's a rule that we apply to the conductor, because we know that typically the overcurrent device is going to be rated for 80%. It's not going to be rated for continuous load. It's going to be limited. Okay. So it's going to be limited. It's not going to be rated for 100% of its rating. Now, there are some breakers that are out there. They are available. And if it is rated at 100%, you're golden. Okay. But most circuit breakers that you and me are going to deal with are all going to be limited and to 80% for continuous loads. Now, if it's a non-continuous load, this is another misconception. If it's a 15 amp breaker and it's a non-continuous load, then I can pull 15 amps on that breaker as long as I don't exceed 3 hours continuously at that maximum current. Okay. So, then it would, because then it would be the maximum current, and it would be 3 hours or more, then it would be a continuous load. So, and that's not how it's going to really happen. Okay. So dwellings, probably not a big deal for anything. Now, I remember that when I talked about water heaters, for example, and things like that, that's branch circuit sizing. When it comes to the feeder, you typically don't take those things with the exception of 220.60, where it talks about heat versus AC, or any non-coincidental load. It's not just heat versus AC. At that point, the new rules into 2020 would say that if the heat is the larger and then the AC was the lesser, let's say, and the air compressor was the largest motor in the dwelling, then the code says that you take that air compressor at whatever the FLC is at 125%, and you add it to whatever the heating load was, and that's what you use in your service or feeder load calculation. That's a change for 2020. I don't like that change, but it is the way it is. Some people agree that it should be written differently than that. We'll see what happens in 2023. But that is what it is. But other than that, don't confuse the branch circuits for branch circuit conductors. Don't confuse that with a service feeder load calculation. Two different beasts, okay? Two different things. Anyway, hopefully you got something out of today's episode. It wasn't too confusing for you. Again, as we talked about ampacity, and we just kind of touched a little bit on continuous loads and other loads within the code that act like continuous loads when it comes to calculation purposes, those type of things. So hopefully you got something out of that, folks. Until next time, stay safe. God bless.
Shut up and sit down.